distinction between the two, or chemistry permits a distinction, because this is chemically different than that. No, it is not. As far as any physical measurements can be made, like energy or any other the chemical rates of reactions and so on, this and this go the same way. That is, you make everything else in a mirror image. This will rotate light to the right, this will rotate it to the left in precisely the same amount. This rotates light to the right a certain amount, and this rotates light to the left, the corresponding amount through the same amount of fluid. So that as far as the physics is concerned, these two amino acids are equally satisfactory, and as far as the chemistry is concerned, they're equally satisfactory. And as far as we understand things today, the fundamentals of the Schrödinger equation have it that molecule and that molecule should behave in corresponding ways, that one is to the right as the other is to the left. Nevertheless, in life, it's all one way. Now, it's presumed that the reason for this is the following. Well, let's suppose, for example, that life somehow is at the moment in this condition, at the way it is now. It's all on a certain side, as all the proteins in some creatures have all left-handed things, and all the enzymes are lopsided. Every substance in the living creature is lopsided. It is not symmetrical. So when the enzymes come, which do the digestion, which change their chemical from one kind to another, this one fits into the enzyme, but this one doesn't fit into the enzyme. It's like the Cinderella and the slipper, except it's a left-hand foot that you're testing. So that as far as we know, it would be possible, in principle, we could, for example, build a frog in which every molecule is reversed. Every atom is twisted. Everything is right to left of a real frog. We have a sort of a left-hand frog. And this left-hand frog would go on all right for a while, but he'd find nothing to eat because his enzymes are built, and if he swallows a fly, the fly's got the wrong kind of, unless we give him a left-hand fly, you see? So as far as we know, the chemical processes and the life processes would continue in the same manner if everything were reversed. But the fact that all the proteins and all the life, from the lowest to the highest, from everything to everything else, always have the same corkscrew, is probably the most brilliant evidence for the correctness of a common evolution of all life. Because if the life is a physical phenomenon, a chemical phenomenon, then we can understand the fact that they're all from the same corkscrew, only from the idea that at the very beginning some few molecules by accident got started, one. Somewhere once, one carbon atom was lopsided a certain way, and from this particular thing is where the life happened to evolve. In that particular geography, that particular historical accident was one-sided. And ever since then, the one-sidedness propagates itself. Once gotten to the state that it's in now, of course, it will always continue. You need the powders to show the beam. When the light hits a mirror, it doesn't go in a straight line again. It goes in a new straight line. It bounces off the mirror into a new straight line, which changes as I change the inclination of the mirror. And the question for the ancients was, what is the relation between these two angles for when I change the angle of the mirror? And it turns out that is, of course, a very simple law, was discovered long ago, and is that the light on a mirror goes in such a way that the angles made with the mirror are equal. Some people, for some technical reason, like to measure the angles from the normal. Those are supposed to be just as equal as the angles from the plane, but it doesn't make any difference. I'll be conventional and measure from the normal, but it's just the same. That was a simple proposition. That law was discovered very early, but the more difficult problem was when light goes from a medium, we have the next one now, huh? When light goes from one medium to another, we have it going from air into water, and we see that it doesn't go in a straight line again. We need some of the powder to show the beam here. And you see that in the water, it's at an inclination to what it is in the air. Now, if you change this angle so it comes down more vertically, then the angle of breakage in the water isn't as great. But if you tilt it up quite an angle, then the angle in the water is so what happens? I don't know what happened. The big question is, what is the relationship of this angle to that? And that puzzled the ancients for a long time. They never found the answer. However, it's in one place in all of the Greek physics that I've ever found any experimental results listed. And here I have found that Claudius Ptolemy gives a list of the angles in the water for each different angle in the air. And here are the angles in the air in degrees. We still use the degrees. He's the guy, in fact, who advertised using degrees. And here's the angle as measured in the water. And this is the result of an experiment. And ordinarily it's said that Greek scientists never did any experiments, but it's impossible to obtain this table of values. without knowing the right law except by experiment. This is the development of physical law then. First you observe an effect, then you measure it, then you list it in a table, then you try to find the rule by which this thing can be connected to that number. So this table was made in 140 AD, and it wasn't until 1600 and something, or 16 I guess, 1621, that finally someone found the rule connecting these two angles. And that was Mr. Snell, and his rule is the following. If this is called the angle in, then this is called the angle out. Then it turns out that the sine of the angle in is always equal to some little multiple of the sine of the angle out, and that for water, this number here is approximately 1 1/3, but that the ratio of the sines of these two angles is everywhere a constant. And that's Snell's law, or the law of sines, and permits us to predict at any moment what way the light is going to come out when it goes from the air to the water. Enzymes digest the right things, manufacture the right thing. When the carbon dioxide and the water vapor and so on go into plant leaves, the enzymes that make the sugars make them lopsided, because the enzymes are lopsided, and so they pass there's no conservation of the number of right-handed molecules. You can once you got started, you can keep increasing them. So the presumption is then that the phenomena in case of life do not show a lack of the symmetry in physical law, but do show, on the contrary, the universal nature and the commonness of the evolution of all the creatures. Now we go further. You say, now look, in the physics there are a lot of other places where you got right and left-hand rules. As a matter of fact, when we learn about vector analysis, we go crazy with the right-hand rules in order to get the angular momentum and the torques and so on, and magnetic fields, and the force on a magnetic field, for example, is Q times V cross B, and then there are screamings about how you must take the velocity this way, the magnetic field this way, take a right hand. But isn't that enough to define a right hand? As a matter of fact, we know, if we look at it again, if we go back and look at where the vectors came from, that it was merely a convention, it was a trick, that the original things, the angular momenta and the angular velocities and things of this kind, were really not vectors. It was just because they were something on a surface, on a plane, and it was just because there were 3 dimensions that we could associate a direction perpendicular to that plane, and we chose the right-hand direction. So if the laws of physics are symmetrical, it should be this way, that if some demon were to sneak into all the physics laboratories and replace the word right for left in every book where the right-hand rules are given, you use always the left-hand rules perpetually, that it should make no difference whatever in the physical laws. Let me give an illustration. There are 2 kinds of vectors then. There are honest vectors, which we call polar vectors. For example, a step in space. If in the apparatus there's a piece of thing here and there's something else here, then in the mirror apparatus, there would be a piece of thing here and something there. And if we draw the vector from the piece of thing to the something, the vector is the mirror of the other one. The vector arrow changes head just as the whole space turns around. Such a vector we call a polar vector. But the other kind of a vector, which has to do with rotation, is of a different nature. For example, suppose that this is the 3 dimensions of axes, and something is rotating around this way, say. Then if we look at it in a mirror, it will be rotating this way, which is the mirror image of the rotation over here. Now, we represent a rotation that way by a vector in this direction here. And we represent a rotation we represent a rotation the same way it is, with a vector this way. So you see that this kind of a vector on a reflection does not change about as the polar vector does, but is relatively reversed relative to the polar vectors and to the geometry of the space. Such a vector is called an axial vector. Now, if the law of reflection symmetry is right in physics, then it must be true that the equations must be so designed that if you change the sign of all the axial vectors, which would be what corresponds to reflection, nothing will happen. So the laws must have this rule, that the equations are such that if you change the sign of all axial vectors, nothing happens. Incidentally, this should include to change the sign once for each cross product, because the cross product also has a signature in it. So for instance, when we write a formula that says the angular momentum is P cross R, that's okay, because if we change to a left-hand system, if we want to change the sign, the polar vectors P and R do not change. The cross product says change once. L we know is a polar vector, change once, so the equation would be maintained. And then all the other equations too. from this, for example, that the force is equal to V cross B. If we change from a right to a left system, then the V must change. That means that B must be an axial vector. Now here's another magnet in a mirror. It's this magnet in a mirror. So the coil will look like this. And everything that happens inside, I don't know how to draw. Well, I'm doing all right, actually. The same coil, exactly, it's a mirror image, and the current will go this way. Now, in the laws for the production of magnetic fields, which we don't know yet, but we have one that says that the magnetic field from a light wave is a unit vector in a direction of observation cross E. So that shows that it's going to be a cross product in the formula for the production of the magnetic field. And there are rules you must have learned in high school about right-hand rules here. So that it turns out that the magnetic field is this way, and that this pole here is a south magnetic pole. While here is going around the other way, and the magnetic field is reversed. It's a north magnetic pole. So you see that when we go from right to left, we must change north to south. But never mind changing north to south, let's talk about phenomena. Suppose now that we have an electron moving through this field. It's coming up from going through this way. I have to draw the projection. Moving this way in the field, it's an electron. Then if you know the formula for the force V cross B, remember the charge is minus, you find that the electron actually has to, in this kind of a field, driven this way, will have to deviate in this direction according to the physical law. So the phenomenon is you've got a coil here with the current going this way, then an electron curves that way. That's the physics. Never mind how you label everything, but this is what happens. Now let's do the same experiment in a mirror. We send an electron in the corresponding direction. Now the forces are reversed because, well, the force comes out in this direction if you figure it out from the same rule. And that's very good because the corresponding motions are mirror images. So the fact of the matter is that in studying any complete phenomena, there are always two right-hand rules, or even number of them, and the net result is that the phenomena look symmetrical. In short, therefore, we cannot tell right from left if we also are not able to tell north from south. However, we can tell the north pole of a magnet. The compass needle, for example, is the one that points to the north. But that's a local business. That's got to do with the geography of the Earth. That's just like talking about which direction is Chicago. So that doesn't count. You say, yeah, I've seen compass needles, or the north-seeking pole is a sort of a bluish color. But that's just the painter, the guy who made the magnet painting it. In other words, if a magnet would have a property that on the North Pole, if you looked at it close enough, you'd see small hairs growing, but not on the South Pole. If that were a general rule, then that would be the end of the principle of reflection symmetry. If there was some unique way to tell the North and South Pole of a magnet, then you could tell which of the two cases you had, and that would be the end of the law of reflection symmetry. To illustrate still more clearly the whole problem, I would like you to imagine that we were talking to a Martian or someone very far away by telephone. You're not allowed to send them any samples. For instance, if you say you do it by light, you could send them right circularly polarized light and say, that's right. So you watch which way it's polarized. You don't give them anything. You just give them information. You talk to him. And he is so far away or in some strange location that he can't see anything that you can see. For instance, you can't say, look at Ursa Major. Now, you see how those stars are arranged? Well, what I mean by right is, and so forth, no? Well, you're only allowed to telephone them, and you want to tell them all about us. Of course, first you start defining numbers, and you say tick, tick, 2, tick, 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 3, and so gradually you can understand a couple of words and so on. And then you begin to after a while, you get very familiar with this fellow, and pretty soon he says, what do you guys look like? So you start, I say, well, we're 6 feet tall. Wait a minute, what's 6 feet? Is it possible to tell them what 6 feet is? Certainly. We say, you know how you take hydrogen atoms, and you know the diameter. 9 billion hydrogen atoms high. So you make 9 billion hydrogen atoms high, it's definite. And that's because change of scale is not something under which the physical laws are invariant, and therefore we can define absolute length. So after defining the size, and we tell them what the general shape is, it's got prongs with 5 bumps sticking out on the ends of the hands, and so on and so on. And everything's going along, and when you're all finished describing how it looks from the outside, from which you have presumably no particular difficulties, in ultimately describing, he's making a model as you go along, you see. And he says, boy, you're very handsome fellows. He said, now what's on the inside? So you start to describe the various organs on the inside, and you come to the heart, say, and describe the shape of it and all. Say, now put the heart on the left side. He says, the left side. Now your problem is to describe to him which side to put the heart, without him ever seeing anything that you see, or without you ever sending any sample to him of what you mean by right. No standard right-handed object. You can't figure it out. And it turns out that the laws of gravitation, the laws of electricity and magnetism, nuclear forces are all okay. They all satisfy the principle of reflection symmetry. But then it turned out gradually, in the new particles that were found, there's a very weak, in all particles, there's a phenomenon called beta decay or weak decay. And one of the examples of weak decay was a particle was discovered let's say about 1956. The following was a puzzle. There was a certain particle which disintegrated into 3 pi meson. As a matter of fact, the first slide shows it's better than a drawing. Here we see a track coming in, and this object goes disintegrating into 3 pi mesons. This was called for a while a tau meson. It disintegrates into 3 pi meson. Now on the next slide, we show another particle which disintegrates into 2 mesons. And this was called a theta. Here it has bounced back from the plate and is disintegrating into 2 mesons. The other one must be neutral from the conservation of charge, but you can figure out where it is from the conservation of momentum and show it's got the mass of a meson. So here we have a particle called a tau, which disintegrates into 3 mesons, 3 pi mesons, and this theta, which disintegrates into 2 pi meson. Okay, thanks for the lights, please. Now, the first thing that was discovered was that the mass of the theta and the tau are almost equal on the what I call the right and comes out on the left, the way the current is going around in the magnet, and that defines the left. So it's possible to define right and left now by doing an experiment of this kind. There are a lot of other features that were predicted. For example, it turns out that the spin, the angular momentum of the cobalt nucleus before disintegration is 5, and after disintegration is 4. And the electron carries this angular momentum out. And so there's also a neutrino involved. But it's easy to see from this that the electron must carry its angular momentum this way, the neutrino likewise. And so it looks like the electron is spinning to the left. And that was also checked. In fact, that was checked here at Caltech by Feynman and Wattstraw, that the electrons spin mostly to the left. There were some experiments that gave the opposite answer, but they were wrong. The next question, of course, was the law of the failure. What is the rule that tells us how strong the failure is going to be? And the rule is this. It only occurs in these very slow reactions called weak decays. And when it occurs, the rule is that the particles which carry spin, like the electron, neutrino, and so on, will come out with a spin tending to the left as they go along. That is, as the particles emit it, it spins to the left from a beta decay. The electron, when it's emitted, spins to the left. That is a lopsided rule. It connects a velocity and an angular momentum, and there's a relation